What's up, my StatsRs? Michael Princhuk here, and in this video, I'm going to do a full summary of Unit 9 over Inference for Slope from AP Statistics. Now, Unit 9 is the final unit of content in the AP Statistics curriculum. Now, let me remind you of two things before we dive too much into the content of Unit 9. First, this is just a summary review video. It doesn't cover every teeny tiny detail of Unit 9. Hopefully, you're actually learning all those teeny tiny details in class. But the purpose of this video is to give you the big ideas that you need to review. That way you can do really well on a Unit 9 exam in class, and you can make sure that you nail all the Unit 9 topics that are on the AP Statistics exam in May. Now, the second thing I'd remind you of is to get out the Unit 9 study guide from the AP Statistics Ultimate Review packet. Everything I discussed in this video, you could then go and practice on your own in that study guide. The study guide's got tons of practice problems from every different topic of Unit 9, so make sure you check it out. If you don't already have it, visit theultimatereviewpacket.com, link in the description. That way you could gain access to that study guide and the answer key to see how you do. All right, let's dive into the content of Unit 9 over Inference for Slope. First, well, what is inference for slope? Well, go back to Unit 2. In Unit 2, we learned about bivariate data. Now, there's bivariate data that can be categorical, or there's bivariate data that can be quantitative. Well, we're going to talk about the quantitative data in this video. Now, the idea is very simple. When you have bivariate quantitative data, you can make a scatter plot of that data, and with that scatter plot, you could create a least squares regression line, and that least squares regression line has a slope. But that slope is just the slope from your sample. That's not necessarily the slope that's going to be true for the entire population from which that sample came from. Well, that's the whole idea of inference. We're going to be using the slope that we got from that sample to make a judgment about what could be true for that population slope where that data came from. Now, if we're going to talk about inference, of course, we need to understand a sampling distribution for sample slopes. The idea is this: when we get our sample data and we find the slope for our regression line, well, that's just one slope from one sample. What if there are many other samples, just like mine, of the same sample size? Every one of those samples is going to create its very own slope. So now what we could do is we could create a sampling distribution to show all of those different slopes. And that sampling distribution has three characteristics: a center, a spread, and a shape. Let's review them all right now. First, the center is the mean of all of those sample slopes. And the mean of all of those sample slopes should be the true population slope, which we'll call beta. Now, of course, the samples have to be drawn randomly to avoid bias. Now, truthfully, we don't know beta, but we can visualize that in the model, the true slope will be in the center. The next characteristic of that sampling distribution is the spread, which we can calculate with the standard deviation. Now, here is the formula for the standard deviation of the sampling distribution for sample slopes. It's a little bit tricky and kind of ugly, but don't worry too much about it right now, and I'll explain more in the video. Now, it starts off with first understand that this is going to be the standard deviation for those sample slopes, lower b. Now, kind of a complicated formula. In the numerator is the standard deviation of the true regression line, and the denominator is the standard deviation of our x values multiplied by the square root of our sample size n. But let's be honest, we're never really going to know sigma. That's the standard deviation of the true regression line. So what we're going to often have to do is use the standard deviation of our residuals in our sample data as an estimate. Same thing, we're never going to know the true standard deviation for all of the x values in the entire population, but we could use the standard deviation of the x values in our sample. So when we build the sampling distribution, we're typically going to use standard error. It's the same formula as standard deviation, but it's replacing those values for the population that we're truly not going to know. So in the numerator, we're going to use S. That's the standard deviation of our sample residuals. In the denominator, we're going to use S sub x. That's the standard deviation of all of our x values in our sample. And then we're going to have a square root of n minus 1. Now, for reasons beyond the scope of this class, instead of using n, we're going to use n minus 1 here. Don't worry too much about it. And in fact, I'm going to be honest, you're never going to really use this formula because this value will be given to you. But again, this is the standard error of the sample slopes. And it's the best we could do. We can't use standard deviation because we don't know all those values. So we're going to have to use the data from our sample, and therefore we could create the standard error. Now, here's some really good news. You're never going to need this formula. Trust me, it is on the AP Stats formula sheet, but it's going to be given to you in a computer regression analysis output table, which I'll talk about a little bit later in the video. Now, the final characteristic of that sampling distribution for sample slopes is, of course, the shape, and the shape is going to be normal. Now, when we actually build the sampling distribution using standard error, we're going to have to use a t-model because, well, we're using information from our sample, the standard deviation of our residuals, the standard deviation of our x's, and not what's true for the population. So that's why t-model is going to be more accurate. Now, when we build that t-model, we are going to need n minus 2 degrees of freedom because we had two variables with bivariate data. So the degrees of freedom is your sample size minus 2. Now, the condition for the shape to be normal is that the residuals must be somewhat normal with no major outliers or skewness. So when you take a look at the residual plot, we want to see, well, nothing. Remember, that's a good residual plot. It's a nice mix of residuals, positive and negative, and they're not all too high, they're not all too low. They're very nice and evenly spread out throughout. So those are the parameters for a sampling distribution for a sample slopes. Kind of confusing, but again, I hopefully you understand the idea of a sampling distribution by now. We have a slope from our sample, but it's just a slope from our sample. We need to at least visualize what all of those other possible slopes from other samples just like ours, same sample size taken from the same population, will look like. And that's exactly what a sampling distribution will do. It'll make a model of what all those other possible sample slopes will look like. Even if we don't know the true slope in the center, it still exists. And we know that our sample slope is somewhere within that model. Now, the next step, of course, is to create a confidence interval for what that true population slope can be. So a t-interval for slope of a regression line is going to be used to try to make an estimate of what the true population slope could be. Let's talk about the 4 steps required to build a t-interval for a slope. First, we have to name the interval in context. It's a t-interval for the slope, and then we have to say what it is we're trying to find the slope of. And then we're going to check the necessary conditions to actually build that sampling distribution, or at least to understand that sampling distribution so that we can actually create our interval. The third step is to actually build the interval, which is by far the easiest step. We're going to use the formula B, that's our sample slope, plus or minus our margin of error. The margin of error is going to be the t star times the standard error of your sample slopes. And then the fourth step is to actually interpret our interval in context. Let's walk through each of those steps individually right now. Step 1 is to name the interval. Again, this is a t-interval for the slope of, and you're going to fill that blank in with what we're trying to find the slope of. Don't forget to use context that is specific to your problem. And we're going to look at an example here in a moment where you actually see me doing this. The second step is to check those conditions. Now, there are quite a few conditions here, and I have to be honest, on the AP Stats exam, usually when they have you do this, they're going to tell you that assume all conditions are met, but we should still walk through the conditions. First, the scatter plot of the sample must look somewhat linear. You would never put a regression line through your data if it wasn't linear in the first place. The sample of observations must be selected randomly to avoid bias. The sample of n observations must be less than 10% of the population from which it was drawn from to assume independence. Number 4, the residuals must be approximately normal with no major outliers or no major skewness. This can be checked by examining a graphical display of the residual values. And then finally, the standard deviation of y does not vary with x. Now, what this means is that when we look at a residual plot, we want to make sure that there's similar variability for each x value. We don't want to see low variability or small residuals in the beginning and then large residuals at the end. We want to see a nice similar pattern, similar variability throughout the entire residual plot. All right, the third step is to actually build the interval. This is, again, I really think the easiest part. We're going to start with the sample slope B, and we're going to go up and down by our margin of error. Now, the first part of our margin of error is t star. You're going to get t star for using invert t on your TI-84 calculator. Just make sure that you're going to incorporate the level of confidence. For example, for 95% confident, the area that it wants at the bottom is that bottom 2.5%. And then it's also going to ask for your degrees of freedom, which is your sample size minus 2 when you're working with slope. And then the other value that we're going to need to multiply that t star by is our standard error of the sample slopes. Now, again, I already talked about the formula for the standard error, but just trust me, you're never going to need it. You're going to be given the standard error in a computer regression output. It's actually literally right next to the slope. We're going to look at that in a moment when we look at an example. And then the fourth step is to interpret your interval. This is where we say I'm 95% confident that the interval from blank to blank, that's the beginning and the end of your interval, captures the true slope of the true regression line relating your y variable to your x variable. And of course, when you actually write this for a specific problem, you're going to fill in the context. You're not going to leave it generic saying just x and y. All right, those are the 4 steps to creating a confidence interval for the slope of a regression line. The true slope, the slope of the population, and we call that beta. All right, hopefully the process makes sense. Now let's look at an example so you can see it all play out. All right, in this first example, we're going to look at a car dealership. A car dealership might have hundreds and hundreds of cars that it has ready to sell. And what we want to do is look at the relationship between the weight of the cars and the car's gas mileage, how many miles per gallon it gets. Now, we want to eventually try to figure out the true slope, the true relationship between the weight and the gas mileage of a car for all of the cars, but we don't have the time to analyze all of the cars. So what we're going to do is we're going to look at 12 random cars from the dealership. And from every one of those 12 random cars, we're going to get the weight of the cars in pounds and the gas mileage measured in miles per gallon. All right, so here is the data. Here are our 12 cars, each with our weight and our miles per gallon. And then of course, we're going to make a scatter plot of this. Now, the first thing I see in this scatter plot is a negative linear relationship. As the weight of a car goes up, the miles per gallon goes down. Now, what I could do is run a computer regression analysis to get the slope and the least squares regression equation for this line. Now, hopefully you remember roughly what this looks like, but here it is right here. Here's one of those computer output tables. Now, from this table, we could build the regression equation. The regression equation is going to be y hat equals 51.17 minus 0.00714 times x. But what we're focusing on this video is the slope. So the slope is negative 0.00714. Now that slope tells me that for every 1 pound that a car increases, the gas mileage is predicted to go down 0.00714 miles per gallon. But that was just the slope for the 12 cars we looked at. We want to construct a 95% confidence interval for the true slope of the regression line for all the cars. All right, so step 1 is naming it. This is going to be a t interval for the slope of the regression line between the weight of a car and the gas mileage of the car in miles per gallon. The conditions are the scatter plot of weight versus mileage showed a strong linear relationship, which we did see in the scatter plot. The sample of 12 cars had to be picked randomly to avoid bias. We have to assume that 12 cars is less than 10% of all the cars to assume independence. And the histogram of the residuals did look to be approximately normal with no major outliers or skewness. So again, I do need to calculate those residuals, but you're never going to actually have to do that on your own, at least for the AP exam. It'll either be told that it's assumed to be true, or they'll actually give you that data. They'll give you that chart. That way you can look at it and say, yeah, there's no major outliers, no major skewness. Find the residual plot needs to show similar variability for each x value. So here, if we actually look at that residual plot, what we notice is that there's big and small residuals throughout. It's not like there's all small in the beginning, all big at the end, or vice versa. It's a nice mix of residuals spread throughout. That's a good residual plot showing no pattern, and that confirms is exactly what we want for that fifth and final condition. All right, now for the formula. Again, this is the easy part because everything you have is here for you. First, what was the slope of our sample? That was the negative 0.00714. Then we have to construct our margin of error. The first thing we need is our t star. So we're going to go to invert t on our TID4 calculator, and it's going to ask for the area. Well, if we're going to do a 95% confidence interval, that's 95% in the middle. That puts 2.5% at the bottom, and that's the area it's asking for, so 0.025. Then we're going to put the degrees of freedom. For this problem, that would be 10 because we had 12 cars, minus 2, 10 degrees of freedom. Now, the next thing we need is the standard error of the sample slopes. But again, you don't have to use that crazy ugly formula to construct it. It's literally right next to the slope in your computer regression analysis. So if you just find the slope in that table, the negative 0.00714, literally right next to it is a column for standard error, and that's where we get the standard error, 0.00056. So multiply that t star and your standard error together, and you get your margin of error. Add it, subtract it to your sample slope, and now we have a confidence interval for what the true slope could be. Negative 0.00839 to negative 0.00589. All right, now it's time to do an interpretation. Based on the 12 cars in my sample, I'm 95% confident that the interval from negative 0.00834 to negative 0.00594 miles per gallon per pound captures the slope of the true regression line relating the gas mileage of the car, y, to the weight of the car, x. Now, that's a little bit generic in a sense, but let's make it actually kind of make more sense. This tells me that in the population, we know that for each 1 pound increase in the weight of a car, the gas mileage will decrease somewhere between 0.00834 miles per gallon to 0.00594 miles per gallon. Now, really, I want you to notice here that the entire interval is negative. So we can be very confident that as the weight of a car increases per pound, the gas mileage is predicted to decrease. And well, that's it. Those are the 4 steps to construct a confidence interval for slope. Now, I have to be completely honest for you. I've never really seen an AP Statistics FRQ problem where you have to run through all 4 of these steps doing all of the work. Typically, what's very, very common is a multiple choice question that just simply says, hey, here is some information for bivariate data. Here's a computer regression output for slope. Go ahead and construct a 95% confidence interval for the true slope of the regression line. And really all you have to do is step 3, using the formula to construct the slope. And I hope you realize that that is usually the easiest part because everything you need is in that table. The only thing you have to go and look up using a t-table or your TI-84 calculator is that t-star, that critical t-value for whatever level of confidence you have. Just don't forget the degrees of freedom is your sample size minus 2. Now, also in Unit 9 is a topic about using a confidence intervals result to justify something about the population. I've actually already kind of talked about that a little bit in this video. Go back to our previous problem. Our entire interval was negative. That gives me very convincing evidence that, well, the slope is negative, meaning that every time a car goes up by a pound, it's going to decrease in its gas mileage. Now, let's just pretend that if that interval was a negative on one side to a positive on the other, meaning that 0 is in the interval, well, that can mean there's absolutely no relationship between the weight of a car and the gas mileage. Because if the possibility exists that your slope could be 0, well, that is a straight horizontal line. That means as x goes up, y doesn't go up or go down. It doesn't really matter at all. So when you have 0 in your interval, it gives you reason to think that there might be no difference. Now, listen, there still could be a slope, a positive slope or a negative slope, but the idea is that 0 is in the interval, so there might not be any linear relationship whatsoever in your data. So it's important to understand that when your entire interval is negative, that means that you're pretty confident that there is going to be a negative slope in the population, and vice versa. When your entire interval is positive, that gives you a lot of good evidence that the slope in the population is going to be positive as well. But when you have a negative to a positive, meaning 0's in there, well, it doesn't mean that we know the slope one way or the other, because again, it's still a confidence interval for what the slope could be, but it just doesn't give us convincing evidence that we know there is going to be, in fact, a slope because, well, negative is possible, positive is possible, even 0 is possible, which means there might unfortunately be no relationship whatsoever. So that's an important thing to understand when you are analyzing the actual interval that you create through this process. Here is another example of this process that actually explains exactly what I was just talking about. Kelly's interested in buying a used car of a particular model. She wants to know roughly how much she should be paying based on the mileage of the car. She examines a sample of 10 cars of this particular model and records the price in dollars and the mileage in miles for each car. Below is a scatter plot and the computer output constructing 99% confidence interval for the true slope. Assume all conditions are met, which is awesome, which means we don't have to run through all those conditions. Now, in this scatter plot, we definitely see that there is a negative relationship. The more miles on a car, the cheaper it is. And we also see in our regression output, we see that the slope right next to the word mileage, that's our x variable. And again, remember, it always goes in order, A on top of B. So A is the y-intercept and then B is the slope. So we see we have a negative slope of negative 0.208. That tells me that for every additional mile that is on one of these cars in her sample, the price drops about 21 cents. Now, let's construct that confidence interval. So step 1 is naming, hey, this is going to be a t interval for the slope of a regression line, predicting the price of a car based on the number of miles on that car. Step 2, we could skip because it said all the conditions are met. Step 3, again, is really the easiest part. And as I've already stated, oftentimes this is a multiple choice question on the AP exam. So we're going to start off with our sample slope. That was the negative 0.2083. We're going to go up and down. Now the first thing we need is our T star. So we're going to go ahead and use invert T on our TID4 calculator. When we're 99% confident in the middle, that means 1% is left out. That's going to be a 0.5% at the bottom and a 0.5% at the top. And the area invert T looks for is the area at the bottom. So that's going to be 0.005 for our 0.5% at the bottom. And then how many degrees of freedom do we have? Well, it said that she had 10 cars, so we have 8 degrees of freedom. And that is where I got the 3.3554 from. And then finally, where did I get the standard error from? Well, again, you don't need that ugly formula. Right next to slope in that computer output is the standard error, 0.0684. Putting all that together, adding and subtracting that margin of error, we get an interval of negative 0.4378 to positive 0.0212. So I'm 99% confident that the true slope of the regression line predicting the price of a car based on the number of miles of that car is somewhere between negative $0.4378 to $0.0212 per mile. Now, let me explain what that means, right? The slope is how much we expect the price of the car to change for each additional mile. So we know that based on this interval, on the left-hand side, it could be negative, meaning that for every additional mile that is on one of these used cars, the price is going to drop by about 44 cents. But on the other side, we have a positive, which means that for every 1 additional mile on the car, it could increase by about 2 cents. Now we also have 0 in this interval, which means that there is a possibility, because any number in this interval is just as likely as any other number in this interval, that we might even have no slope whatsoever. So the price or the mileage of a car goes up, but the price doesn't change at all. In fact, it doesn't even matter. So if I were asked, is there convincing evidence of a negative slope? More miles, price goes down. I would say no. The interval actually shows it could be positive. More mileage means the price goes up. Or the interval contains 0, which means there might not be any relationship whatsoever. So this is a good example where I could actually see that based on the interval, I can't make any clear-cut justification about what's true for the population because it could be negative, could be positive, could even be 0. But just another good problem to walk through the 4 steps and actually see how to build that interval for the slope of a regression line. Next up in Unit 9 is a significance test for the slope of a population. Now here, we should be very familiar with a significance test. The whole idea starts off with somebody making a claim about what is true for that slope of the population. And then we're going to have to determine or gather evidence based on our sample to determine if we have evidence that that claim is true or if we have a lack of evidence that claim is true. So there should be 4 very, very familiar steps at this point. Step number 1 is to name the interval and give the hypotheses, which we'll show you in one moment. Step number 2 is to check the conditions and create that sampling distribution based on the null hypothesis being true. Step number 3 is to calculate our t-score and then get our p-value. And step 4 is to make a final conclusion based on that p-value. Let's walk through each of those steps right now. Step 1, we're going to name the significance test. This is a t-test for the population slope. And then we're going to give the hypothesis. So it's going to look something like this. So the null hypothesis is that the slope we were told was true is still true. So you got to read the problem. Maybe it said that they thought that the true population slope was 5 or 3 or 6 or negative 1.4. So then that would be our null. So when I'm putting beta sub 0 here, that's just the null hypothesis slope, what we read was true in the problem. And the alternative is what we're claiming. We think that the true population slope is greater than that value, less than that value, or not equal to that value. Now, however, I gotta be honest, in most AP problems, we are simply looking for evidence to support a claim that there is, in fact, a linear relationship between the two variables. We don't care what the slope is, we just care that there is, in fact, a slope. So oftentimes the null hypothesis is that the true slope is equal to 0. Meaning that there is no relationship between the two variables. So we assume there's no relationship whatsoever, and then therefore the alternative hypothesis is that the true slope is either greater than 0 if we believe the slope to be positive, or less than 0 if we believe the slope to be negative. Now, we don't have to use a 0 here, right? It could be an actual value that you read from the problem. But again, oftentimes we're just analyzing, is there even a relationship between these variables? And if we're just trying to figure out if there's a relationship or not, that simply means that there is a non-zero slope. Something greater than 0, positive relationship, less than 0, negative relationship. All right, step 2 is to check the conditions. These are the same conditions that we checked for a t interval as well for slope. So a little bit boring, but again, I gotta be honest, I've seen a lot of AP exams in the past, and very few of them, if any, actually incorporate you having to check all these conditions. There are a lot of them, and some of them sound familiar, but I just want to make sure I emphasize that fifth one more time. In the residual plot, we want to see no pattern. We want to see a mix of residuals with similar variability, meaning we don't want to see a fan pattern. We don't want to see large residuals all going down to small residuals in the residual plot. We want to see a nice mix of large and small residuals showing similar variability throughout the entire residual plot. All right, next up is actually building the sampling distribution. This is also in step 2. So we have to go ahead and find the mean and the standard deviation. Well, we typically don't use standard deviation. We're going to have to use standard error. Well, because we only have our sample data to work with, so we're going to have to use that data. But again, this is stuff that we already know, and it's all going to be given to you in one of those computer output analysis charts. So first, what is the null hypothesis? Well, the null hypothesis typically, as I just mentioned, is that there is no slope whatsoever. There's no relationship. So we would assume that the center of the sampling distribution, the mean of all possible sample slopes, is in fact 0. Then we're going to calculate that standard error. And once again, here is the formula for standard error of sample slopes. But again, you're never going to need it. You're just going to be given to it in one of those computer output tables. Once again, let's go back to our weights of our 12 random cars, and we want to determine, is there even a slope? Is there even a relationship? We look at our sample of 12 cars, we look at the weights, we look at the gas mileage, and we clearly see a scatter plot that shows a negative relationship. As the weight of a car goes up, the gas mileage of that car goes down. Okay, that's obvious in our sample, but is that what's true for the population as well? Well, that's where we would use this sample data to construct a confidence interval, as we already did, but we could also use this sample data to do a significance test. All right, so if we're walking through this problem, we would first say, okay, step 1, this is a t-test for the slope of regression between the weight of a car and the gas mileage of a car. The null hypothesis would be that there is no slope whatsoever. The true slope beta of the population is equal to 0. No relationship, right? Weight of a car goes up, gas mileage doesn't change at all. Sometimes it goes up, sometimes it goes down, who cares? But the alternative is what we believe. We clearly believe from our sample that there is in fact a negative relationship, and we think that the slope of the population of all the cars is going to be negative, which means less than 0. And then in the second step, we do have to check all those conditions. Gets a little bit boring, I know, but I'm going to just say for maybe the 4th time, you don't have to check all these conditions. They're usually going to be assumed to be true. That's the good news when it comes to the AP exam. All right, now that we understand steps 1 and step 2 really well, let's take a look at steps 3 and step 4. So step 3 is actually getting our test statistic, our t-score, and then using it to calculate our p-value. So here is the formula for that t-score. We're going to take our slope from our sample B, and we're going to subtract the null hypothesis slope, which in most cases is going to be a 0. And then we're going to divide by the standard error, again, that is given to us in that regression analysis output table. All right, once we have our t-score, we could go ahead and create our p-value. Now, remember, we're going to use our TID4 calculator for this. We're going to do a t-CDF because we're using a t-score. So when we use t-CDF, we're going to use our t-score. If it's positive, we're going to start with that, and we're going to go to 999 or 99, just something to act like infinity. If it's a negative, we're going to look below it. So we're going to start at negative 99, acting like negative infinity, and we're going to go to an upper value of our t-score. Then we need the degrees of freedom. The degrees of freedom, again, is your sample size minus 2. So in our sample that we're working with right now, we had 12 cars. 12 minus 2 is 10 degrees of freedom. All right, then we're going to make our conclusion. Our conclusion is based on that p-value, and this should all be very familiar from units 6, 7, and 8. If our p-value is well below our significance level of typically 1 or 5%, we are going to reject the null. And when we reject the null, that means we do have evidence that the alternative is true and that there is in fact a slope, a relationship between these two variables, whether it be positive or negative, depending on your alternative hypothesis. And then if our p-value is greater than our significance level, well, we fail to reject the null hypothesis. We do not have evidence of a slope between these two variables. We're not saying that there isn't a slope or that the slope is zero. We're just saying we don't have evidence that we could officially say there is in fact a slope. I mean, there still might be, we just don't have the evidence to support that conclusion. All right, let's look at how we could conduct these third and fourth steps in our example looking at our 12 cars. All right, so step 3 would be saying, all right, let's get that t-score. So we're going to take our sample slope. That was the negative 0.00714. We're going to subtract 0. That was the null hypothesis. That was what we assumed to be true, that there was no slope whatsoever. And we're going to divide by that standard error, which once again is in that computer regression output. And we get a very low t-score of negative 12.75. So now we're going to find our p-value. Our p-value is the probability that any other sample slope B is less than or more extreme than ours. Ours was a negative slope, so or more extreme would be even more negative. That's going to be the probability that a t-score is less than negative 12.75 in a t-model with 10 degrees of freedom. So when we get that p-value using TCDF, we're going to start at negative 99. We're going to go to an upper value of negative 12.75, and then we're going to have 10 degrees of freedom, and we get a very low p-value of 0.000000824. Now for our conclusion. Since our p-value of 0.0000824 is less than 0.01, we will reject the null hypothesis. There is statistically significant evidence that a negative slope exists between the weight of a car and its gas mileage. There is a linear relationship where the more a car weighs, the lower its gas mileage is in miles per gallon. We don't know exactly what that slope is. We could do our confidence interval that we did earlier in this video to actually estimate what that true slope could be. But again, that doesn't mean we still know what it is. But remember, from that interval, we do know it's negative, which does support our conclusion here that there is, in fact, a relationship. All right, let's look at one more full example to see how a significance test for slope can be conducted. Now, in this example, researchers performed a study where they examined data from a random sample of 16 babies from the United States. For each baby, they measured the age in days of when the baby first began to walk and the average daily temperature in the city of where that baby lived. So we're trying to see if there's a relationship between the temperature of where a baby lives and how long it takes that baby to walk. Now, when we look at this scatter plot, we first off notice that, well, the relationship isn't extremely strong, but we do see a slight negative relationship, which shows that as the average daily temperature increases, that the amount of days it takes a baby to learn to walk actually goes down. All right, so the question is there in fact a relationship? Because you got to understand the idea that when we look at a scatter plot like this, we could say, all right, there's two reasons for why we're seeing what we're seeing. We're seeing a negative relationship because there really is a negative relationship. In warmer temperature cities, babies learn to walk faster. Or we're just seeing a relationship because, well, you throw 16 dots at a wall, you might see some kind of relationship just by pure randomness, and it doesn't necessarily mean anything. And that's exactly why we're going to conduct a test to determine what that reason is. All right, so step 1 is going to be to name the hypotheses. So we're going to conduct a t-test for the slope of the regression line between the average daily temperature of the city the baby lives in and the number of days it takes the baby to begin to walk. Our null hypothesis would be that true slope is 0. There's no relationship whatsoever. Temperature goes up, number of days the baby learns to walk doesn't go up or to go down, it's 0, it doesn't matter. Versus alternative that we think there truly is in fact a negative relationship, because that's kind of what we saw in our scatter plot. All right, the next step is to check all of those, sorry for saying it, boring conditions, but again, they are necessary. And then to actually build that sampling distribution following the parameters of our problem. So the mean of all possible sample slopes would be 0. Where do we get 0 from? That was the null hypothesis. We always assume the null hypothesis is true when we conduct a significance test. And then the standard error, that's going to come right from one of our computer output tables that we saw with this data. So don't have to do all the work for it. Now it comes time to actually calculate our t-score and our p-value. So our t-score is going to be taking the slope that we saw in our data, negative 0.5055. Because again, in our data, we did see that as the temperature goes up by 1 degree in the city that the babies live in, that they actually learn to walk about 0.5 days faster or quicker. Now, we're going to, of course, take our sample slope and subtract 0 because we assume there is no slope whatsoever. And we're going to divide by that standard error that we got from that computer regression output table. And this time we got a t-score of negative 0.6126. So our p-value is the probability that any other sample slope B is more extreme than ours. Ours was negative, so in this case it's going to be less than that. That's going to be looking at a t-score less than negative 0.6126 in a t-model with 14 degrees of freedom. So we're going to use TCDF to find that value, and we get 0.2769. Now our conclusion with that p-value is going to be to fail to reject the null. That p-value of 0.2769 is greater than either 0.01 or 0.05, so there is no statistically significant evidence that there exists a negative linear relationship between the average daily temperature of the city a baby lives in and the number of days until that baby walks. The relationship we are seeing is most likely due to just chance. Again, we kind of knew that from the very beginning when we looked at our scatter plot and saw, well, it's not really the strongest relationship, but this significance test confirms that yes, we did see a negative relationship in our data, but that doesn't necessarily mean there's a negative relationship in the population. And when we fail to reject the null, well, we're basically saying that we do not have any significant evidence to officially say that as the temperature goes up, babies will learn to walk faster. All right, so that's it for the summary review video for Unit 9 over inference for slope. There are two key things that you have to be able to do. Create a confidence interval for what the true population slope could be between the two variables, and conduct a significance test for analyzing, well, if there's even a relationship between those two variables. So hopefully I explained the process pretty simple. They both involve the 4 steps that we've seen before with intervals and that we've seen also before with significance tests. Just make sure that you know the steps, but also know this, and just kind of be honest here. On the AP exam, you typically are not going to have to run through everything. Usually every single year, I see one multiple choice question that asks you to create a confidence interval for slope. And they give you everything you need. They give you that computer output table that has in it the slope and right next to it the standard error. You just have to be able to recognize them and find them. And the other thing that you will have to calculate on your own is that t star, that critical value using either a t-table or invert t on your calculator. Just make sure that you remember how to do that and make sure that you know the formula with slope is sample size minus 2 for degrees of freedom. Now, with a significance test, every now and then it does come up on one of the FRQs, but typically it's a small part of an FRQ where you don't have to run through all of the steps. But again, I wanted to make sure in this video I talk about every teeny tiny detail of all of those 4 steps, but typically on an exam question, you might not actually have to do all of them. You just have to do a lot of the interpreting. So hopefully that this video did a good job of explaining all that interpretation for you. All right, see you in the next video.